Now we'll learn about wave characteristics. This will help us define a wave using the properties of the wave or its characteristics. So some characteristics of waves, such as a large water wave that's shown here, are based on its geometric features, and some are based on time. Waves can be described in terms of their size, their shape, and the speed at which they move. Wave characteristics based on shape and size, those geometric characteristics, include amplitude, wavelength, phase, and phase shift. The maximum displacement of a vibrating particle in a wave from its equilibrium point is called the amplitude. And the amplitude, when we have that amplitude reached above the equilibrium point, or the line of vibration, we call that a crest. That would be something like what we see here. This would be a crest. And if we have an amplitude that's below, we'd have a trough, which would be like what we see here. This is a trough. For a longitudinal wave, we have compressions and rarefactions, and basically the amplitudes occur at these points here. So our amplitude would be the point between when we reach, it's kind of hard to see the midpoint here, so you could say it's the half of the distance between each compression, but that is our that is how we determine amplitude in a longitudinal wave, although we won't be seeing that too often. A wavelength is the distance from the start of a wave cycle to the end of a wave cycle. So for a transverse wave, we can start it at a point when it's at the equilibrium point, and then when it moves through its trough and crest, or crest and trough phase, back to the equilibrium point. That is a full cycle. For a longitudinal wave, the wavelength is the distance between any two compressions or any two rarefactions. This question here says to sketch a periodic wave consisting of two complete wavelengths with a lambda, which is a wavelength of 4.0 centimeters. Label the diagram with amplitude, crest, trough, wavelength, and equilibrium or rest position. I can let you try this on your own. This question says, what type of vibration do we have? If we have a pendulum moving like that, it's moving perpendicular to its rest position, so that is a transverse vibration. What is the amplitude of vibration? So the amplitude of vibration is the distance from the rest position to its maximum displacement, either on the left side or the right side. 17 divided by 2 would be 8.5, and that would be our amplitude in this case. What is the total distance the mass moves horizontally in 5 cycles? So a cycle would be this pendulum bob moving back here and back. So it would be a back and forth kind of motion. So it would have to do this motion each time, and if we're doing that 5 times, that would be 17 times 2 times 5, which is 170 centimeters. We mentioned it earlier, a phase shift, but what does that mean? What does phase mean in terms of a wave? So we could have waves that are essentially identical in wavelength and amplitude, but they might have had different starting times. So they could have a shift in when they started. We call that shift a phase shift. So this first wave would have, these two waves are identical in wavelength and amplitude, but because this wave started earlier than this wave, there is a noticeable shift in the phase of each wave, or where those waves have started. Time-based characteristics are related to the motion of the vibrating particle and the wave. These characteristics are frequency, period, and speed with which the wave travels. Our frequency is how many cycles do we have per unit of time, and this is usually in cycles per second. And a cycle per second is given the symbol Hertz, which is a capital H Z. Sorry, the symbol is a lowercase f for frequency. The unit is Hertz, which is capital H, lowercase z. They're named after Heinrich Hertz, who is the German scientist who first produced electromagnetic waves in the laboratory. The frequency of the wave is exactly the same as that of its source. So if we have a source that's vibrating at a specific frequency, then the particles that vibrate in the medium would vibrate at that same frequency. The opposite of frequency is the period. This is how much time we have, or how much time it takes for a certain number of cycles. And period is measured depending on the phenomena we're looking at. Period could be measured in seconds, it could be measured in days, it could be measured in years. But period, again, it's the time it takes for a number of cycles to occur. So the other interesting thing about this is frequency and period are reciprocals of each other. So your frequency is your n, number of cycles per second, divided by your t, your time, and your period is your time divided by the number of cycles. Sorry, I should say that again. Frequency is the number of cycles per second. N is your number of cycles divided by t, which is your time. And for period, t is your time divided by n, which is your number of cycles. Although if you have the period and you need to find your frequency, you can just reciprocate it. And if you have your frequency and you need to find your period, you can find the reciprocal of the frequency as well. This question says, a mass is attached to the end of a spring that vibrates 15 times in 12 seconds. And it asks us to find the frequency and the period. So if we have something that vibrates 15 times in 12 seconds, that's 1.25 hertz. I guess it should be 1.3 for rounding for significant digits. The period would be the reciprocal of that. So if you can press just your reciprocal button, and we get 0.80 seconds. Calculate the frequency of a CD player that rotates 4.5 times 10 to the 3 times in 1 minute. So that is 4,500 times in 1 minute. That's 60 seconds. We'll want to write this in hertz. We have a 75 hertz frequency for that CD player. This question says, if the moon orbits the Earth 6 times in 163.8 days, then what is the period of revolution? So our period is how many, it's basically the time it takes for the cycles to happen divided by those cycles. So it's 163.8 days. Sorry, I gotta redo that. 163.8 days divided by 6. I'm going wrong there. 163.8 divided by 6. We have 27.3 days. That is our that's our period for the moon in this case. Two identical pendulums are said to be vibrating in phase if they have the same period and they pass through the rest position at the same time. Otherwise, they're said to be out of phase. So if we have something that is in phase, they will hit their crests and their troughs and their equilibrium point all at the same time. If they don't, then they are out of phase. Which pair of pendulums are vibrating in phase? So A is on the left side and it's moving to the right. D is on the left side and it's moving to the right. So A and D would be in phase. List all pairs of points that are vibrating in phase. This is a little bit harder. So we have one wave. Which of these points are vibrating at the same phase? You would have to kind of look at what their location is on the waveform. A is here, so it's a little bit behind, or a little bit after A, you hit the equilibrium point going up. The next point that is like that would be E. B is a little bit after that equilibrium point, and so it would match with F. C, we don't have another point that matches where C would be. And the same thing for D. The point for D should be over here, but we don't see that. This question says, as you walk, describe the movement of your arms and legs as in phase or out of phase oscillations. So your left arm, if you kind of notice how you walk, usually your left arm is swinging when your right leg is moving, and your right arm is swinging when your left leg is moving. So your right arm is in phase with your left leg, but out of phase with your right leg, and your left arm is out of phase with your left leg and in phase with your right leg.